Hello Math 1100 students, here's the final lesson of the course. Lesson 14, Exponential and Logarithmic Models. There are many models, but we are going to focus upon these four. Let's go to the first model, Compound Interest Model. It looks like this. Suppose that you invest a principal of P, say $1,000, with annual interest rate R, 2.5% for example, compounded n times a year, 12 times a year each month, or 4 times a year each quarter, kind of like that, and let it rest for a number of years. Then the balance will grow because the interest will keep compounding in, and what we have is this expression there. Now, how in the world do we get this expression? That's something to discuss a bit later. Let's talk about how to use it first. Principal is P, the initial investment, and R is the interest rate, annual interest rate. And the annual interest rate versus monthly interest rate. Use your common sense. What's the best way? Of course, dividing by 12. And that's what this is, R over 12. Now, if it is quarterly reinvesting, then R over 4. Daily reinvesting, then R over 365. Get the picture? And then how about the power? N times T, that's the number of months. So we are compounding each month. So you have to use monthly interest rate, not the annual interest. So we have R over N. And then we are compounding by months. So we have to count number of months, not number of years. So we have N times T. And I use months as a representative when n equals to 12, but you could use the same logic for a number of quarters when n is 4, or number of days where n is 365. Theoretically, you can do it for every minute or second. In that case, n will be humongous. That's something to discuss as a matter of fact. When n is humongous, does it mean this whole expression is blowing up to infinity or something? The answer is no, it doesn't. It becomes, voila, the natural exponential function. And that is the reason, this is a key reason why this kind of topic appears in the math book. This is one of very good ways to explain students how the natural exponential function arises in real life application. Compound interest, well, that happens all the time. And then when we consider compounding very, very often, each day, or each hour or minute, or second, you can consider those kind of things when number of reinvestments grows to pretty close to infinity. And we have this kind of limit. And we have 1 plus R over N. And R over N should be considered as one quantity. And we need the reciprocal there. So with some algebraic manipulation, we have something like this, where the natural exponent base E is, roughly speaking, 1 plus 0 power, 1 plus 0 to the infinity power, roughly speaking, where the 0 part and infinity part should be reciprocal of each other, like 1 plus 1 over k plus in the k power, 1 plus h to the 1 over h power, like that, either way. Exactly how this thing is coming into play is something we'll have to discuss in calculus. We talk a little bit about this in calculus 1, but most of the discussion about natural exponential will be differs to calculus 2 or higher. So for now, you'll just have to take for granted. And here's one formula for continuous compounding. And here's another formula. This is a little bit more practical when we have periodic compounding. So every quarter, 4 times a year, every month, 12 times a year, every day, 365 per year, kind of like that. Okay, so much for the theory. We have yet to prove it, yes, but we're going to come back and discuss it later. Let's go over to an example problem here. Let us solidify our understanding through an example, and then if you have some time left, then we can come back and do some proofs. Okay, here we go. We have this formula there, of course. And here's the setting. Suppose that you're investing $1,000 and investing in an investment CD with fixed annual interest rate of 5%. Now, if the interest rate varies, then this thing becomes a whole lot more complicated. You have more than one variables here, so things are far more complicated. But here we have fixed interest rate, fixed annual interest rate of RE equals to 0.05, 5% here. And then n value is given differently. Yearly, n equals 1, quarterly, n equals to 4, monthly, n equals to 12, and daily, n equals to 365. So, what do? You just calculate this thing, pick up your calculator, and just do that. So, 1,000 times 1 plus 0.05 over, say, 12 to the 12 times 7 years. And then calculate it, punch into the calculator, you're going to get the answer for the balance for monthly reinvestment. Now replace this by 4, then you're going to get the answer for quarterly reinvestment. If you go to a commercial bank, most of the time you're going to see a quarterly reinvestment. Sometimes you see monthly reinvestment, but most of them will be quarterly reinvestment setting. By the way, here is mathematical program for that. Instead of typing everything in, I wrote a program. It's not really a program, excuse me, no, just a command. So these are the balances. Of course, with same annual interest rate, daily compounding gives you the best value, and just once a year doesn't give you too much. And the difference between one and the other is not that much actually, less than $20. Okay, all right, so much for just direct calculation problem. Now, here's a little bit more significant problem. How many later will the initial investment doubles? I could have written not just double, or 1.5 times the original, or 3 times the original, or 2.6 times the original. I could have deferred a little bit, but let's keep it as double. So I start from 1,000, and then t years later, it has doubled. Basically, that's what you have to do. And of course, this is not something you can solve precisely. So you're going to end up with approximate equation here after punching the calculator. Excuse me. And then, of course, you'll have to repeat this for yearly, so reinvestment once a year versus quarterly, 4 times a year, monthly, 12 times a year, and daily, 365 per year. So you have problem number 1 here. Second problem. Third equation. And then fourth equation. So basically you have to solve these 4 equations. So if I just do one, can you do the others? You should be able to do that. Okay. I have the one down here already highlighted, so I'll do this one. And I'm going to leave the others to students. Fair? Okay, let's go from here. Let's solve this equation with respect to t. Now let's come back to the original equation. And numbers are too big, so let's begin with some simplification. We have these 3 zeros here and 3 zeros on the other side. You can cancel those out. Basically, I'm dividing everything by 1,000 by, from both left-hand side and right-hand side. And then, of course, times 1 doesn't make any change, so let me just remove that. So we have much simpler equation here. Okay, we have an exponential equation, so what do you do? The first thing you should do, excuse me, one more thing. It says 5% of annual interest rate, so network was a little bit unstable. So for the moment, I thought I would lose this mathematical. Luckily, I got it back. Okay, all right. Previously, I just had R there, but the problem gave you R values. So, and I just replaced those R by 0.05 for all those 5%. Okay, now we have those 4 equations, and then we are working on the fifth equation here. Okay, let's solve this. Now, this is an exponential equation, so we have to remove the exponential, and in this kind of practical problems, the modeling problems, the only logarithm you have to consider is going to be the natural logarithm. The other kind of logarithms are okay for previous week. In week 13 or week 12, we study those kind of things. But here, natural logarithms only. So what am I going to do? I'm going to take natural log of both sides. And then log of this quantity. Does it make sense? I took the log of both sides. Now, will this improve the equation? Yes, indeed it will. Look carefully. Log of 2 on the left-hand side, of course, everything is all set, no problem there. In the right-hand side, you can apply a log rule. This power comes out as coefficient, and then you have this log of this quantity, 1 plus 0.05 over 365, this quantity. So what do we have? We have now an algebraic equation. This logarithm here just a constant. If you punch into calculator, you're going to get some number, and that's about it. 365, that 2 is just a number. I can always flip it over to the other side by dividing it away. And I have only one t here, so I'm in business here. Just divide everything out. So t is log of 2, which was there before, divided by the coefficient I had here, 365, and then log of 1 plus 0.05 over 365. And all I have to do is to punch this into calculator. And that's going to be my answer. Does it make sense? The key is to take log and then using the log rule here. So, exponential equation, just go ahead with natural logarithm. And then if you remember those log rules, then the problem will take care of itself from this point on. The power comes out as coefficient, and then what do we get? We have 365 times this log, whatever the value is. Those are all numbers. Just flip it away, and you're going to get t value. So what is this t value here? Log of 2 divided by 365 times log of 1 plus 0.05 over 365. 13.86 something according to this computation. So it'll take about 13.86, nearly 14 years to double the money if you use daily compounding. For monthly compounding or quarterly compounding, or even worse, just once a year, annual compounding, it'll take even longer. The answer keys here. Okay, we have 4 equations, 4 solutions. Just once a year takes more than 14 years. The best is daily compounding, still almost 14 years to double. Okay, we are not completely done with section 1, so let's stop here and we'll discuss the rest in the second video.